Alright guys, let's start on section 4.4. Now there are two very short videos that you should have watched before this. One was reflections into parallel lines and one was reflection into intersecting lines. So if you haven't watched those videos, please watch them. They're each less than 2 minutes, so you're talking less than 4 minutes, because it really kind of gives a visual of what this section is all about. Alright. So let's look at what the reflections in parallel lines theorem tells us. So just like the video explained, it tells us that if we start with BA, we reflect it over line K, and then we reflect it over line M, what we get is line B double prime, A double prime. And when we do this, it tells us that this is just simply a translation from AB to A double prime, B double prime. In that translation, if the distance between the two lines is D, that means the distance between A and A double prime is 2D, and the distance between B and B double prime is also 2D. Okay, so that's very important to note. And remember, just by process of, or just by the rules of reflections, that means if we connect A to A double prime, we have a right angle and a right angle. And then also if we connect B to B double prime, these are also right angles too. Okay, and also just because we have reflections, we know that this segment is the same as this segment. And then we know that this segment is the same as this segment, and then same on bottom too. So just know your rules of reflections as well. All right, let's look at example 1. So it says in the diagram, a reflection in K maps GH to G prime H prime. So we take HG, we reflect it over this line, we get H prime G prime. Then we reflect it again over this line, we get H double prime G double prime. Okay, and then it goes on to tell us that HB is 9 and DH double prime, so this here is 4. All right, so now we're going to do A, B, and C. So A says, name any segments congruent to each segment. So GH. So GH is right here. Well, we know that when we reflect, it's a rigid motion, so we have congruent segments. So from GH, we know that GH is congruent to G prime, H prime, right? It's congruent to this, and it's also congruent to H double prime, G double prime. So I'm just going to put it like this. All right, now let's look at HB. So HB is right here. Okay, so properties of reflection tell us this here is going to be the same length as this here. So I could say HB is congruent to H prime B. And then let's look at GA. So GA is right here. Okay, and we know that rules of reflections, that means it has to be equal to that. So I'm just going to write GA is congruent to AG prime. All right, let's look at part B now. It says, does AC equal to BD? Okay, now I'm going to come through and just delete or erase a lot of that. All right. So does AC, so AC is right here, equal to BD? Okay, well, it looks like it, but hopefully we've learned by now we can't assume something if we can't prove it. So what I need you to do is I need you to think about the properties of reflections. Okay, so we know when we reflect, if we connect 2 points, it crosses them perpendicularly. So this is a right angle, this is a right angle. And likewise up here, from here to here's a right angle, here's a right angle, here, all over is a right angle. Okay, now I want you to take a look at this figure right here. Okay, we have a quadrilateral that has 4 right angles. And so what is a quadrilateral with 4 right angles by definition? By definition, a quadrilateral with 4 right angles is a rectangle, and we know that one property of a rectangle is that opposite sides are congruent or equal. So we can say that AC is equal to BD. So I could say yes, because ABCD is a rectangle because of what I just explained. And if we had this on a test, I would expect you to explain it. And on a rectangle, opposite sides are equal. All right, let's look at part C now. It says, what is the length of G prime? It should be G double prime. Okay, now remember that theorem. So remember the theorem tells us that the distance from one point of the beginning, so like here, all the way to the end, or from here all the way to the end, it's going to be double the distance from the two parallel lines. Okay, well, we were told in here that HB is 9 and that DH is 4, and I must have erased that. Okay, so if HB is 9, that means B to H prime is also 9, which means the distance between these two lines is 13. Okay, and now back to this theorem. This whole thing is double that, which is what that first video showed you. So if this whole thing is 13, this has to be 2 times 13, which is 26. All right, here's example 2. Now, I want you to go and try to do example 2 on your own, and then we'll go over it. There is a typo here. This should be P and P double prime. Okay, so use the properties you know about reflection in lines and use the theorem we just learned about the reflection in two parallel lines, and you should be able to come up with the answers to A, B, and C. All right, so let's go over this. You should have gotten all these. These were just like the example before, and these weren't too hard. So if we went straight from P to P double prime, that theorem we just learned tells us it's just a translation. And the relationship between P prime to line K, I should have said it is also perpendicular. Okay, so first of all, it's perpendicular. I didn't write that, but I should have. Second of all, the distance from P to line K is the same as the distance from P prime to line K. And those are just the properties of parallel lines. And the distance from P to P double prime, well, guys, that theorem, the reflections in two parallel lines theorem, tells us that that is double what the distance is between the two lines. So if the distance between the two lines is 1.6, the distance between P and P double prime is double that, so 2 times 1.6 is 3.2. All right, so this is the theorem that goes with that second really short video that I had you watch before you watched this video. And it just talks about when you reflect a point or a figure or whatever twice over two intersecting lines, what you get is a rotation. So from here to here, you get a rotation that is double the angle between the two intersecting lines. All right, so let's do a real quick example. So we know that we reflect F over line K and then reflect it again over line M. So what we get is F double prime. So it wants to know, describe a single transformation that maps F to F double prime. Okay, well, if this angle is 70 here, we know that theorem tells us that it is the same as a rotation that is double this. So 2 times 70 is 140 degrees. So it's just a rotation around, or that's at, so rotation around, I'll just write it out, around point P, 140 degrees. All right, go ahead and do this one on your own. It's very, very similar to the one we just did. All right, you should have got that it is a rotation about point P that's double this. So from here to here would be 160 degrees. All right, let's go over a couple vocab words, and you probably could figure these out by yourself without going over them, but we're going to go over them anyways. So congruent figures are just what they sound like. They're two figures that are congruent. So by definition, they're figures where there is a rigid motion or composition of rigid motions that maps one of the figures onto the other. Now, the important thing is they have the same size and they have the same shape. Okay, and that a congruence transformation is just another name for rigid motion, which is also called an isometry. And it basically tells you that the image and the pre-image are congruent figures. All right, this one's pretty simple. It just says identify the congruent figures. So which of these figures are the same size and same shape? So that's my explanation. And I'm not going to write them. I'm just going to highlight them. So this figure and this figure are congruent figures. This triangle here and this triangle here are congruent. And then this triangle and this triangle are congruent. All right, so now we're going to have to kind of think backwards on this one. Okay, so it says we want to describe a congruence transformation that maps triangle JKL, so that's this triangle in blue, to MNP. Okay, so how do we make this go to here? Okay, well, the first thing, and there's a couple ways you can do this, so if you would do it different, that's fine. So the first thing I see is a translation. Okay, so if we translate this, I don't know, 1, 2, 3, 4, 5, 5 right, and then not up or down, so I can say x, y goes to x plus 5, y. What we would get is this would be here. J would go 1, 2, 3, 4, 5, so J would be right here, J prime. And then K is 1, 2, 3, 4, 5. So here we are. Okay. Now from here, if we reflect this, and we would just reflect it over the x-axis, right? And it would go here to here, here to M, and K to N. So reflection over the x-axis. And that's all I would have to write for that. All right, I want you to do this one on your own. Make sure you read the words. If it helps you, draw pictures. You should draw a picture in geometry always. And then we'll go over it. All right, so let's go ahead and do this. So it says a rotation of 76 degrees maps C to C prime. So if this is C, I don't know, let's make this our point of rotation or center of rotation. And then my C double prime is 76 degrees this way, so C or C prime is. Okay, and if I were to draw it, oh, that was bad. Guys, these tablets are really, really hard to draw on. So let me try this again. If I were to draw it from C, that looks better. This is 76 degrees. Okay, so this is asking me to map C to C prime using two reflections. What is the measure of the angle formed by the intersecting line? So we're going to reflect it over here, and then we're going to reflect it over here to get C prime. Okay, so here to here, here to here, that's how we do it. So if we go back to this theorem here, okay, the full rotation is double the measure of the angle in between. So if this is 76, the angle in between would be 76 divided by 2, which is what, 38 degrees? And that would be your final answer.